Hello guys, welcome to my fourth class of inner product space. I know I am repeating so many times because of the students. So please try to understand. I'm also go through very slowly. And then why? Because of our student. This is our class like that. You try to understand what I'm going to explain. Okay? Yeah. Now I'm moving to the one of the problem. Given u dot u is 39, v u dot v is equal to minus 3, v dot v is equal to 79 they given. Find inner product of u plus 2v comma 3u plus v. Now, I want to find out this. First I have to simplify for the given what they given form. Therefore, what I'm going to do here, I'm consider this. Anyway, there is a you and we are taken from the inner product space. You just assume that is clear. From the second and third conditions or axioms of inner product space, this can be written as u comma additive concept in the first slot u comma 3u plus v inner product of 2v comma 3u plus v. Again you have to apply in both the cases additive property in the second slot u inner product of u comma 3u plus inner product of u comma v plus inner product of what actually 2v comma 3u plus inner product of 2v comma v, and then use the third condition is nothing but homogeneity for the first and second slot. Now we get 3 into u inner product of u comma u. This is inner product of u comma v only. This is nothing but 2 also take and 3 also take. 3 2s are 6 inner product of v comma u plus 2 into inner product of v comma v. These are the things are written from the condition definition or condition of IPS means inner product space. Now 3 into inner product of u comma u, then you know that inner product of u comma v, then this can be written as from the symmetry from the definition of inner product space v comma u can be written as u comma v. Add these two we get inner product of u comma v. Inner product of u comma u means u dot u. Inner product of u comma v means u dot v. Inner product of v comma v is v dot v. They given already, substitute and simplify. Now I get this problem in one of the articles. Suppose they are going to ask how to do it. That's why I am discussing here. Next problem. Determine all the vectors in R power of an Euclidean space with n dimension that are orthogonal to u having a vector. How many components? 2 components, 4 comma 2. You see, determine all the vectors in R power of n. See, this is not R power of n. Actually, determine all the vectors of not R power of n. What's the dimension here? 2. Therefore, what we am going to take here? R square. This is nothing but R square. Euclidean space with the dimension is 2. Euclidean space with dimension is what? 2. That are orthogonal to u is equal to 4 comma 2. They given one vector. You have to find out what is the orthogonal vectors of 4 comma 2 with the dimension is 2. Is a Euclidean space means is a set is a vectors are real numbers. Then given u is given u 4 comma v. See, what's the meaning of orthogonal vector? Inner product of u come any mutual vector must be equal to 0, but I and j is not equal. Then I may choose another vector, say v, having how many components? 2 components. How I have taken 2 components? Because the given vector having 2 dimensions, this also 2 dimension. Consider vectors u and v are orthogonal. Just assume that they given orthogonal. For what vector? U must be an orthogonal. That's why consider the vector u and v are orthogonal. Then that implies u comma, what's the meaning of orthogonal? Inner product of u comma v must be equal to 0. Means u dot v is equal to 0. Then u dot v is equal to 0 means 4 into v1 plus 2 into v2 must be equal to 0. Now that implies what we get actually v1 must be equal to, after the simplification, minus half into v2. Now to give the different value of v2 we get different value of v1. That's why they get determine all the vectors in Euclidean space with dimension 2 that are orthogonal to this. Don't get it one vector. Give the different values. See, V1 depends upon V2. Give the different values of V2 in set of real numbers, we get the corresponding V1. Therefore, let V2 is equal to T. What is my V1? Minus T by 2. Therefore, now V is equal to minus T by 2, comma T. Yeah. Now give the different values of what about the T? We get different value of V. That's why they are asking determine all the vectors that is orthogonal to U is equal to 4 comma 2 in R square. Therefore, where T is a set of real number. This is a way to find out another vector that is orthogonal to the given vector. Yeah, that's also is not given in any question paper. Suppose they are going to ask how to do it. Therefore, even though it's a simple, I consider all different type of problems here. The next is show that the following function is not an inner product space on R cube. Means with the dimensions, it's a set of real numbers with dimension is 3. Euclidean space with dimension is 3. That's all. And also they define what is UV. UV is, suppose U is having 3 vectors U1, U2, U3. V is having 3 vectors, say V1, V2, V3. Then they define already inner product space between U and V is nothing but U1, V1 minus 2, U2, V2 plus U3, V3. I think it's clear U and V having 3 components because both are coming from the vector space with dimension is 3. Yeah. Now, see, then they show that it's not a inner product space, means it may be not satisfy any one of the axiom or any one of the condition of inner product space out of 4. Therefore, here I taken one of, say, V is equal to 1 comma minus 2 1 belongs to R cube. We say, yeah, 3 components, I'm going to use that. Then what is inner product of V comma V is nothing but B dot P. What is B dot P? 1 whole square. What about that? See, now we can't take 1 whole square like that. V dot P, use this inner product of V. U1 V1 is 1 into 1 only. Yeah. V1 and V1 same thing, minus 2 into U2 V2 means minus 2 into minus 2. What we get actually minus 2 into minus 2 is plus 2. That's why I written 2 only. Plus what is the next one actually? Now if you want to write, this is actually minus, this is minus, okay? Yeah. Then is a minus. Oh, okay. Plus 1 into 1. After the simplification, we get negative value. Negative is less than 0, but is less than 0. But in the fourth axiom, inner product of V comma V must be greater than or equal to 0 for V belongs to R cube. This is not satisfied the fourth axiom of inner product space. Therefore, the given function is not a inner product space on R power of on what actually R power of 3. I think everyone is clear. Then it must be satisfied any one of the condition. Then we say that the given defined inner product space function, given inner product function is not a inner product space. Therefore, the for it's not satisfied. So, thus the given inner product function is not an inner product space on R3. Euclidean space with dimension is 3. I think everyone is clear for this. Now I'm moving to the next problem. Yeah. Now before moving to the next problem, I want to discuss some different type of notation they given in David Seeley. The vector 0 is said to be orthogonal to every vector. Means 0 vector is orthogonal to every vector. Keep in mind. Yeah, because 0 vector comma non-zero vector, what is that value? Must be 0 only. That's clear, everyone, you know that. That's why I written in the note. Next, U is a vector having n vectors, but they taken in the column, and V is having n vectors. A vector U1, U2, etc. Un R power of n is represented as n cross 1 column matrix. They take, instead of up to that we are consider row form, but here they consider column. Therefore, U dot V means inner product of U comma V is nothing but U dot V is nothing but U transpose into V. Yeah, I told this one in the beginning class of inner product space. Suppose the vector they given in the form of column. Usually in David Seeley they given in the form of column. Then what is inner product of u comma v is u dot v, or if you want to find out u transpose of v. Both are given as same thing. That's it, the thing I explaining in the note. Yeah. Next is show that the following the following set of vector is a basis for R power of 4 Euclidean space with the dimension is 4. They given S having 4 vector 1, 2, 3, 4. Each of the vector having how many components? N components, because they are asking what's a Euclidean space, what's the dimension is 4. Now we say basis means first I am going to take this is V1, this is V2, V3, V4 for my convenient. Now first I have to verify whether these vectors are non-zero. Yeah, observe carefully, these vectors are clearly non-zero vector. I think everyone is clear. V1, V2, V3, everyone is a non-zero vector. Fine. Is a non-zero vector. Next I have to verify that is orthogonal. Suppose is an orthogonal, yes is an orthogonal set, immediately say that is a linearly independent and also span, therefore is a basis. That basis called orthogonal basis for the R power of 4. Therefore, what we are going to do here, first I am to observe these vectors of S are non-zero vectors. Clearly V1, V2, V3, V4 are non-zero vectors. Therefore, first I have to verify whether these vectors are orthogonal vectors. Means S is an orthogonal set. How to verify is orthogonal set? I have to take the inner product of V1 into V2. V1 into V2 means what? 2 into 1 plus 3 into 0 plus 2 into 0 plus minus 2 into 1. Simplify that, we get 0. Similarly, I have to take V1 with V3. 2 into minus 1 plus 3 into 0, 2 into 2 plus 2 in minus 2 into 1. Simplify that, we get 0. Similarly, I take V1 with all combination. V1 with V4. 2 into minus 1 plus 3 into 2 plus 2 into minus 1 plus minus 2 into what about that 1. Simplify that, we get 0. Then another combination is V2. V2, V3, find out V2, V4 and also V34. You know how to find out dot product. You find out, we get 0. Therefore, S is a orthogonal set. Then you know that S is any non-zero is a non-zero orthogonal set itself is a basis for corresponding vector space. What's a vector space? For V means what? R power of 4. Therefore, S is a basis for R power of 4. This basis called what type of basis? Is a orthogonal basis for R power of 4, because the vectors are non-zero orthogonal vectors. I think it's a very one clear. And also written in the note, I told in my previous video, if V1, V2, etc. Vn is an orthogonal basis of V R, orthogonal basis for Euclidean space with dimension n, I choose any vector in vector space, then W can be written as C1 V1 plus C2 V2 etc. Cn Vn, where Ci is equal to inner product of W comma Vi divided by half whole divided by norm of Vi square. Yeah, for I. For I is nothing but I is equal to 1 to n. This is a formula we have to remember. Suppose that express any vectors in the form of orthogonal basis. Are you clear? Yes. Now I'm moving to the last problem here. I'm discussing all types of problem. Please try to understand. Just now I discuss how to verify is a basis. It is enough to verify the given set is a non-zero vector, and also I have to verify is a that set of vectors are orthogonal set. Then immediately from that result we say that is a linearly independent and also span. Therefore, S itself is a basis for R power of 4. That basis called orthogonal basis. Yeah, next moving to the next problem. The set S is having 3 vectors where they given in the form of, purposefully I taken in the form of column. The student must be familiar. They are going to ask the question in vectors having a coordinates in the column form instead of row form. Yeah, row vector or column vector. U1, U2, U3, they having a dimension is 3, is an orthogonal basis for RQ, because Euclidean space with dimension 3, because each vector having 3. Express the vector Y is 6, 1, minus 8 as a linear combination of vectors in S. They given already what they taken the vectors for S, U1, U2, U3 are is an orthogonal basis of R cube, is an orthogonal basis for Euclidean space of dimension 3. Then I have to choose one of the vector in R cube. I have to express linear combination of U1, U2, U3. They asking. Yeah, express in the linear combination vectors in S means U1, U2, U3. I told just few minutes before, from the definition of orthogonal basis, I choose any vector in R cube that can be written as linear combination C1 U1 plus C2 U2 plus C3 U3. But what's a C1 formula? Inner product of W is Y comma U1 divided by inner product of U1 U1, and then similarly inner product of C2 is Y comma U2 divided by inner product of U2 U2. And also next I have to take inner product of C3 is nothing but Y comma I is equal to 3, that's all, Y comma U3 divided by inner product of U3 U3. That this is a way they find out the values of C1 C2 C3. Suppose these vectors are orthogonal basis. How to find out that C1 C2 C3? Just now we derived the result for orthogonal basis. Okay. Now, first you find out y comma u1. You have y, you have y1, y dot u1. If you want to find out directly, you take transpose of that. Y dot u1, 6 into 3 plus 1 into 1 plus 1 into minus 8. Okay. Y comma u2 means y dot u2. Y dot u2 means what actually? 6 into minus 1 plus 1 into 2 plus minus 8 into 1. You simplify that, we get. Similarly, inner product of y comma u3 means y dot u3. 6 into minus half plus 1 into minus 2 plus minus 8 into 7 by 2. Simplify that, we get minus 32. Similarly, find out inner product of u1 3 square plus 1 square plus 1 square, and then you inner product of u2 minus 1 to 1, and then you have to find out 1 minus 1 whole square plus 2 square plus 1 square. Simplify that, we get. And then you find out inner product of u3 means what actually? Inner product of u3 means what we get actually? Minus half whole square and then minus 2 whole square plus 7 by 2 whole square. Simplify that, we get this. Substitute these values in C1. What's a C1 formula? Inner product of y comma u1, substitute, and inner product of u1. Then like that we can C2 C3. Then y can be written as linear combination of what is C1 is 1 u1, C2 is minus 2 C2, and then minus 2 C3. Keep in mind this type of problem is very important. They given already say S is having some set of 3 vectors. These vectors are orthogonal basis for Euclidean space with dimension 3. Then they taken one of the vector in R power of 3. Then I have to express that vector in the linear combination of S. Means first you find out C1, C2, C3 using a formula inner product of y comma ui divided by inner product of ui. Just now I derived in this result. Now based on that put W here y, because in the formula we have taken v, here v is equal to y. Then see I is equal to 1, I is equal to 2, I is equal to 3. Simplify. This is way to express linear combination of vectors. Suppose the vectors are orthogonal basis. Suppose choose any vector in the corresponding inner product space. How to express? This is one of important problem. Here they given vectors are column vector. They may be given in the row vector also. Method is same. Thank you very much for listening my talk. I'll come and meet in the next class. The new topic is nothing but orthogonal projection. Yeah, before listening the next video, I'm requesting everyone recall, refresh for definition of inner product space, norm, and dist of between the two vectors u and v, and orthogonal set. And then suppose S is a orthogonal set and all the vectors are non-zero vectors in the inner product space, that vectors are linearly independent and also basis for the corresponding inner product space. Means that's a orthogonal basis for the inner product space. Suppose the given vectors are orthogonal basis. Suppose choose any vector in the inner product space. How to express in the linear combination of these vectors? How to find out C1, C2, C3? These things you recall and then come and listen next my video is nothing but actually based on orthogonal projection. Yeah, in the next tomorrow I'm going to upload some more videos based on orthogonal projection, orthonormal set, orthonormal basis. And then once you complete this, next is only two topics. One is Gram-Schmidt method, another one QR factorization method. Now, even though I have a notes you already download from my website, I'm requesting everyone, you please go through what I'm going to upload the material along with the videos, because I return once again in the modified and also in very compact and easiest form. Thank you very much for listening. Thank you. If you have any doubt, you please mail me, or you please put any comments in my uh, WhatsApp in late 2020. Okay. Thank you. Bye. See you.